Leon Fleming D'Souza, working as an FPGA design engineer at Prodigy Technovations. Today, we are going to discuss about a new product that is UFS 4.0 exerciser. Let's get into the hardware setup. The Prodigy UFS exerciser consists of 2 transmitters and 2 receivers. It also has a ripper socket where you could place your UFS device for validation. Simply connect the transmitter from the TX terminal and receiver to the RX terminals and then power on the exerciser board using the Type-C cable. These are the specific connections required for exerciser board. Now let's dive into the features of Prodigy UFS exerciser. First and foremost, it acts as a host emulator, supporting capabilities up to gear 5 speed, enabling you to validate your UFS memory devices with confidence. The Prodigy UFS exerciser seamlessly integrates with Prodigy M5 UniPro UFS protocol analysis software. Now, let's look into the software application. We have added a new view to the software called the exerciser view, specifically designed for the Prodigy UFS exerciser. The exerciser view allows you to control and configure the device just like you would with the analyzer software. Let's talk about the scripting language used here. This language is very easy to use and user-friendly. All you have to do is select the packet you desire and run it. There is a feature to load a script. All you have to do is go to the custom path where your script is located, select it and save it. As you can see, we have set a preloaded script that we would like to run and test. Let's explore the M5 layer settings. As you can see on the screen, here you can make adjustment to various M5 state parameters including prepare, sync, trailing clock, intermessage gap, which adds a gap between 2 frames, line reset and idle time. These settings are configured using the provided packet. All you need to do is load the script and run the scripts. Let's consider an example. By default, the data rate will be set to PWM. Let's write the script in such a way that the prepare value of D2, trailing clock value of 0732, idle time of 0900, intermessage gap of 0FF, and line reset of 038A. These values can be easily customized to meet your requirements. Additionally, we offer the option to send M5 and UniPro layer packets. You can also send UFS layer packets too. Let's take an example of link startup sequence. Let's set the trailing clock value to 0FA0, which means the period of the trailing clock will be for specified duration. Next, we'll add an intermessage gap with a value of 0. This indicates that there should not be any gaps between the 2 frames. Let's change the value to 0F, which indicates there will be a gap of F number of cycles between the 2 frames. Then, we'll add a line reset command with a value of 7238. This indicates that the line will be in reset for the specified amount of time. Finally, we'll set the idle time with a value of 3FF0, which indicates that the bus will be idle for this duration. Now, we choose the packet that you prefer to send. Let's focus on LSLSS. I would like to discuss the link startup sequence. First, all you have to do is select the configuration packets and run them. Then we have to run the script in the PACP view and you can see the PACP packets that are sent from the host to device and the device has responded back to us. Let's look into the UniPro view. You can see that we have set the various trigger UPR0 packets and the device has responded with UPR1 packets. This indicates that the link startup has been successful. We'll also have a capability to extend packets, which indicates the maximum gear that the device supports. Here, we have received information from the device stating that it supports a maximum gear of gear 4, along with the respective prepare length and sync length. Let's look at the PACP capability extend packet sent from the host. The host has the maximum capability of gear 4. An important feature is that we can change the capability extended packets according to your requirements. We can also verify the marker timing by assigning the line reset to a specific value, which corresponds to a duration of 3.21 milliseconds. In essence, the line reset remained active for the entire 3.21 millisecond duration. If you want to switch from PWM to the desired gear, all you have to do is send a PACP power request. I have loaded a PACP power request script. As you can see, there is a full control over number of bytes in the PACP data. If you would like to run it in the fast auto mode, you have to write 8C 8C, whereas C corresponds to gear 4. If you want to run it in the fast mode, you have to mention 2C 2C. So, whatever response you get, it will be running in the fast mode. Let's run it in the fast auto mode itself. Send this PACP packet. I would like to run it in gear 4 and then I would like to send a UniPro packet to gear 4. Let's have a look at UniPro data. Let's choose the default mode, set the byte count to 23, enable the CRC value to true and let's run it. Here, you can see the script of the configuration packet. Here we have specified the prepare value as 10, which is in hexadecimal. So it corresponds to 16. We have sync length of FC and trailing clock as mentioned in the earlier scripts. Here, we can see the power request packet sent from the host has been responded to by the device with the confirmation. Let's write a script for UniPro data. As you can see, there are several sections like prepare, sync, SOB, EOB, data, PACP packets and so on. Let's focus on the data section. Once we select data, we will have three choices: default, custom, incremental. The default section will have to set the value for the DL data to be sent. In the custom section, you can write your own data. In the incremental section, there are a set of patterns such as numbers and series in an incremental pattern. Let's go with the default option. I will provide a byte count of 32 and enable the CRC value to true. Then let's run it. As you can see, the device has responded back to us with an opt-in packet. We can check the UniPro data that we have sent in UniPro view. When we send a UniPro data, we also send AFC by default. AFC is sent in response to what device responds back to DL data. We send the AFC as a form of acknowledgement. As you can see, I have entered a packet type called knopout, which is a UFS command. There are different types of packets that you can enter, as you can see in the drop-down. Let's choose command. In the command section, there are many command types, as you can see here. Let's take the read10 command. Write down the script required for the command. Add the flags, LUN, expected data transfer length. As I would like to read 4 KB of data, I will give the expected data transfer length as 1000. I would also like to read the logical block address with the value of 0000001. Then I will choose the transfer length as 1000. If other parameters are not required, you can leave them alone. By default, they will be set to 0. Now let's run it. As you can see in the UFS view, we have sent the read 10 command. You can see the frame view. Let me send it again. We can see that the device has given us a response. Here, we have seen the data in response that we get from the device. You can also see the 4 KB data here. Let's look at the write 10 command. Load the write 10 command and let me specify a few other commands as well. So I will set the query request set flag and I will run it. As you can see, the query request set flag appeared in the UFS view. I will then send request sends. I have received the response from the device for the request sends, and now I will make the write transaction. As you have seen, we have made a write transaction, so I have filled in the respective script. Now I will send the data out. So I initially sent write 10, which basically indicates to the logical block address of 0000. Now let me write that 4 KB of data to the particular logical block address of 0000. As you can see, the device has responded to us with a ready to transfer, which indicates that the device is ready to accept the 4 KB of data. Let's look into the error injection capability. Let's set the script here. I will inject a false CRC value and I will run it. You can observe the CRC error in the UniPro view. Let's select the UniPro view and when I select the packet, you can see the error marked in red. If you select the red block, you can find the actual error here. As seen, the actual error is mentioned here. The required CRC was BCFF, but it was set to FEBC. In this way, we can inject CRC errors in the UFS exerciser. You can analyze the captured traffic in CSV format, providing you the detailed insights into the performance of your UFS memory devices. We also have a support for UFS and UniPro layer CTS. Thank you. That's all for the demo.